So De Morgan's is, remember we had one before? This was before the midterm. Neither nor is the same as. Remember I used equals?
Either or.
No, neither. I neither go to the game nor eat a hot dog. That means I'm not
Going to the
game and
not eating a hot dog.
so neither nor is equivalent to that. This, not this, and not that, right?
Yeah.
The other one was not both. That equals not both the Red Sox. What is the playoffs? I don't follow sports.
I don't know.
Kansas
Baseball,
City?
yeah. Not both the
Royals?
Royals and Mets, right? Mets win the World Series. That's true, right? Not both of them win. Meaning,
One of them loses.
not this wins or not that wins, right? So that's De Morgan's, that transformation for prior to the midterm, for just the stuff we've been dealing with. De Morgan's for quantifiers after the midterm, our new logic, is basically this with quantifiers. This is the true symbol for equivalence. That's your two-way street. Yeah. The biconditional is actually not strong enough for equivalence. If you guys remember, there were some examples where you see these two things and they're not quite saying the same thing. But I said before, you can think of the biconditional saying they say the same thing. That was kind of a lie. It's about as close as we're going to get. The true symbol for equivalence is this. This is way beyond the course, but that's just why I got it, since we're at that stage where I can kind of give you this, okay?
Did you want your flash to be on?
No.
We good?
Mm-hmm.
All right, so these are equivalent, that's what that, okay, so here we go. Not everything is P, remember the example I used last time, I'll use that again, is the same as, is equivalent to something is not P. So make it concrete. So the classroom here, remember I told you I went to school in Wisconsin, very homogeneous, right? So not everyone in this classroom, let's do it right here in Hawaii, right? Not everyone in this classroom is what?
Asian.
No, but it's Hawaii. Who do you expect?
Asian.
Yeah, Asian, Hawaiian. No, most people in Hawaii are not Hawaiian, right? Most people are what?
Local.
Okay, sure. Not everyone in this classroom is local. Suppose someone says that, right? Why is that true? Because you need. Suppose someone comes in and says, "All you guys, you guys is local, right?" And someone goes, "No." So it's not everyone in the classroom is local. Why? Because there's
At least one person
who's
not local.
not local. You guys with me? Okay, these are equivalent, but it doesn't depend on your knowledge of being local or being Asian or whatever. It's just whatever P. It's when you say not everything is P, whatever the P is, that's equivalent to something is not P. You can substitute in any example you want and it'll make sense, but the point is this holds in general. We good? Okay, any questions?
No.
Another example? No, okay. If you get that, then these are variations on the theme. So let's try this one. This one says everyone in the classroom is
Black.
no, this is the same example.
Sorry.
Not local. Okay, imagine that. Everyone in this classroom, not local. What would they look like?
All white and pasty.
All foreigners.
Well, maybe not. But okay, maybe they're all from the Midwest or down south. Hey, y'all, right? Or maybe they're all Chinese. I can't speak Chinese, sorry, but you know what I'm saying, right? No one's insulted. Yeah. Okay. Japanese, you're fine. I'm Japanese. Oh, don't get sounds the same to me. Well, sorry, not the same. Sorry, I know. Yeah. You got me on recording. I shouldn't do that. So everyone is not local. You understand? We're imagine it, right? That's the same as.
Not.
Yeah. What is that? What is that?
Not someone.
No, it's not everyone. This is not everyone. That's the mistake everyone makes. Not someone. What is not someone? No thing. Not thing, right? Not something. No thing. That's literally what nothing is. It's a contraction of not and something. No thing. Nothing. No one is local. So when you say everyone in this class, imagine it. They're not local. That means nobody in the class is local. Make sense?
Yes.
Okay. Not everyone. People confuse with this, and everyone is not, they confuse with that, but this is the whole point of De Morgan's. If you memorize the patterns, you won't make that mistake. Like people, okay, good? Again, you think meaning, give you an example, it'll make more sense. This is the hard one, but it's just an extension coming out of that. So again, let's use the same example. Everyone in the class, I claim, is not local. So you imagine it, they're all Caucasian or all Chinese or all whatever, right? They're just not local, right? And someone says, is it true that everyone in this classroom, so look at it right now. Is everyone in this classroom not local? No. So you say it's not true. So not the case that everyone is not local. Why? Forget this one. Everyone in the class, I make the claim, everyone in the classroom here is not local. And someone says, that's not true. Why? Because someone is, right? So right here. Take away the two nots, if I take away the not, right? So not everyone is not local is the same as someone is. You put this in English, it's confusing. Not everyone is not local, but make it like this. Everyone in the class not local, and you go, no, that's not true. Why? Because someone is. Make sense? A little bit? Okay, these are the two that you encounter the most. This one not so much. You should memorize these two because they show up pretty much throughout the rest of the course.
Is it easier to just not deal with the third one? Because that's just a double negative and my brain just does not.
Yeah, double negatives are a bit difficult. That's why don't worry about this one too much. It doesn't show up, but these do. Yeah. Good? Questions? Okay, here's the point. This is about the only pattern you get for the second half of the course, in addition to the all blah blah, some blah blah. After that, it becomes pretty much all art. Meaning, since it's case by case, you got to understand the meaning, right? That's what we're emphasizing for the second half of the course. You're not going to get these sort of patterns that you can sort of mechanically just click in and check out and not even understand. If you understand the meaning, all this stuff starts to go together much more quickly. But there are patterns or forms there that underlie the various meanings. This is one, and the all blah blah and some blah blah is the other one. The rest is just variations on those themes. Yep. Good? We good?
Yes.
Okay. Everyone know what I should always ask? Do you know what I'm using terminology here that you may not be familiar with? Ask if you got any questions. But variation on theme, I've used that before. Is everyone clear with that? Does that make sense? No? Okay, so a theme is it's a musical analogy, but if you're not, if that doesn't make sense, think of it like as a dish, cooking. Like what? Give me an example.
Pasta.
Anything.
Like
Spaghetti.
kongi.
Okay, kongi. Oh, kongi is not, it's just rice, right?
Yeah, but it's what you put in it. I mean, you
There you
have
go.
the basis of your rice and then.
So what's a
you put-
variation on kongi?
Yeah, it's a variation.
Or better yet, yes, there's pasta. Pasta, what's a variation on pasta?
Spaghetti.
Spaghetti, what's another variation?
Alfredo.
Alfredo, what's another one? Ramen.
Ramen.
They're all the, yeah, in fact it stems from China, right? And then it goes to Italy and that's sort of the origins of it. So these are all sort of variations on the same kind of thing. Likewise here, when I say variations on theme, it's the same kind of underlying pattern, but you're switching it up just slightly, you're spicing it up. And that's what you see a lot in logic. If you get the forms, then you're going to see a lot of sort of variations on those basic forms. Kind of good? Okay, moving on. Other stuff, that's the point. Besides these patterns and the all blah blah, some blah blah, other stuff is just that. It's case by case. There's no general guidance. Here's an example. Everything is P and Q. By the way, remember I told you the all tends to go with the arrow and the E tends to go with the and, but you can have cases where the A goes with the and. The problem here is this is really strong. So you're saying everything is P and Q. That's the same as everything is P and everything is Q. So you can think of this as like distribution, right? Just like when I had, I erased it, but distribution, you think AX goes to the PX and AX goes to the QX. You got that? Does it distribute through? Yeah, the answer is yes. Let's use a concrete example. Everything is a cube and small. So what does that look like? What does that world look
A
like?
bunch of
Everything
small.
is-
Just small cubes and nothing but small cubes, right? So when you put and there, this actually makes it too strong. You're not saying all cubes are small. That's different. All cubes are small, can have other objects in there, right? Just the cube's got to be small. This one's saying everything is a cube and small, no choice. It wipes out any other object, just all small cubes, okay? So if you imagine that world, that's the same as everything is a cube, and also everything is small. So in this case, it works out. You can actually prove that this goes back and forth. You know, from if you assume this, you can prove that, and if you assume this, you can prove that. Good?
Yes.
Okay. So you might think, okay, what about or? Everything is P or Q. So can't I distribute through and get everything is P or everything is Q? And the answer is actually no. Here's a counterexample to show that these are not equivalent. So suppose I have for PX, dodec X, and QX, 10X. It doesn't really matter. Q, I mean, just choose those two shapes, right? So this says every object, each object is either a dodec or, okay, so imagine the possibilities for that. I could have all dodec world. Is it true that each object is a dodec or tet?
No.
No, for all dodec world, is it true that each object, when I check them, they're dodecs or tets?
Yes.
Yes, because when is or true?
When
When
one
one
side
At
is
least one is true. Do I have at least the dodec being true?
Yes.
Yes, so this actually is okay with all dodec world, right? Because every object I check, I ask, check this object, is it a dodec or tet? Yes, it's a dodec. Check this object, is it a dodec or tet? Yes, it's a dodec, because it's all dodec world, right? Now, on the other side, imagine
All tet
all
world.
tet world. Is it also true that everything is a dodec or
Yes.
a tet? Yes. What does it also allow for? One
Allows
other
for
type of
both.
world. Mixed world. If I have dodecs and tets mix up, is it true that each object is a dodec or a tet?
Yes.
Yes. Okay, so this allows for three possible scenarios. All dodec world, all tet world, mixed world. You good?
Yes.
This one says what? Everything is a
PV.
Dodec.
dodec or everything is a
Tet.
tet. So either everything's a
Dodec.
or
Everything's attached.
Can I have mixed worlds?
No.
No, because it says everything is, right? If I have both of these true together, that's like having a strange hybrid. You can't be Doric Tet at the same time, right? So this disallows that. That shows that they're not equivalent. They don't say the same thing. Make sense?
Yes.
Okay, good. The rest is practice. That, I'll come back to it later. All right, here we go. Open up your books. Page 281, I would think. 10.22 is first. Oh, where's the... Oh, there it is.
No. There's nothing. It's kind of like a mirror. It's like a window. It's not a mirror. I don't know.
Is it 1022?
Yes.
Okay, so that's page 282.
What
That's
page?
scary, man. You're sketching out.
Yeah.
So I guess it's
It's at
No.
oh yeah.
1022, right?
Yeah, 10.22.
So that's 282.
282?
Yes.
Okay. Okay, open up Church's sentences in Ramsey's world. Church is important for something called the lambda calculus. You actually get that, I don't know, I doubt you get that in intro linguistics, but when I talked about the minimalist program last time with Chomsky, you actually get some of that. Forget it, it's not important for you guys. Anyone here going into programming? No, okay. You do any programming in higher order languages, in fact any language, it's based on what are, programming languages are what make computers operate, right? Java, there's a whole bunch. When you study the structure of how languages are put together, you're going to talk about eventually the lambda calculus. That's what this guy Church did. It's a basis for pretty much all programming languages and how programming works. There's an intimate relation between logic, the development of computer science, linguistics, the stuff we talked about, and they all sort of come together in these unexpected ways. Interesting stuff, but for much higher levels. So keep that guy in mind if you go on higher. Church, where is it? Church's sentences, there it is. Enlarge it. Okay, and it says then open up Ramsey's world. We talked about Ramsey before, or Frank bumped in Ramsey. Decision theory, why insurance companies profit off you, even though he didn't intend that at all. Okay, here's the deal. So you can read through all this and that's great, but here's the bottom line. It's saying, make one change to the world that messes with these sentences. So before we do that, before we make the change, let me try to explain what's going on here. So let's call in you guys for the hell of it. All right, nah, forget it. Everyone's off this. This is like a bye week. Everyone, what does the first one say?
Everything is a large.
Everything is large. Is that true?
Yeah.
Yes.
Yes. And what does 2 say?
A is large, and C is large, and C is
Is that
large.
true?
Yes.
So you notice that when you say everything is large, that's kind of like and, right? If you're saying everything is this, then you're saying this and this and this or whatever, right? The older notation for the universal quantifier, instead of the upside down A, used to be this, a large and. And they used to put some predicate P sub I, and they'd index it I equals 1, 2, dot, dot, dot. It goes on forever. So if you say everything is large, in this case your P is large X, and then subscripted, right? Then you're saying this is large and that's large. In this case, A is large and B is large and C is large. Whatever, however many things you got in your world. With me so far? Here's the point though. While the universal is like an and, they actually aren't equivalent. Because this and is different from our and. This and goes on in principle forever. Okay? Our and always has to come to a stop. So if I say everything is large, that means large A and large B and large C, no further, right? So it's like an and, but not equivalent, okay? Why is it not the same? That's what we have to show. Likewise here, the existential, what does that say?
Something
Something is small. So what does 4 say? Is that true, by the way, when you look at the world?
No.
No, what does 4 say?
A is small, or B is small, or
Because
C
when you
is
say
small.
something is small, you only got 3 objects, so you got to relegate it to those 3, right? So if you say something is small, it's got to be A or B or C, right? The existential, EX, That's like what? When is that? What does that mean? Something. When is something true?
When
At least one, right?
One.
At least one is saying this or that. So existential is like an or, so the order notation was a big or with whatever, but it's not exactly the same. So when I say something is large, that means A is large, or B is large, or C is large. It stops there. We good? Okay. So the existential is like an or, and the universal is like an and, but they're not exactly the same. So the assignment says, if you read it, add one object to the world such that 1 and 2, so when I verify it right now, by the way, take a look, 1 and 2 are both true, and 3 and 4 are both false. So you might think, oh, they're equivalent because 1, everything is large, that's the same as A is large and B is large and C is large. So aren't they saying the same thing? And likewise, 3 and 4, 3 says something is small, that's false because there's nothing that's small, right? And if you say something's small, it's got to be one of those 3 objects. So A is small, or B is small, or C is small. So aren't they saying the same thing? Well, the point here is they look like they're saying the same thing. The universal is like an and, the existential is like an or, but they're actually not equivalent. Add one object to the world. I just hit new and I put that in and add that small cube. Okay. Now take a look. Is everything large?
No.
No. But is A large and B large and C large?
Yes.
Yes. So there's a mismatch showing that 1 isn't equivalent to 2. They aren't saying the same thing, right? The universal is actually much more powerful than just a simple finite enumeration. And likewise, 3 is something small?
Yeah.
Yes now, but is it A that's small or B that's small or C that's small?
No.
No, so when you verify it, you get the mismatch. That's what the book is asking for. 1 is false, 2 is true, 3 is true, 4 is false, showing that these aren't equivalent and those aren't equivalent. Okay? This is also, by the way, why we can't do truth tables for the second half of the course. If we did, if we said, we did a truth table for something like EX, large X, right? And we did that. The problem is when you say something is large, you're saying either A is large or B is large or ... It goes on in principle forever. Something is large means just one of these things has to be true, however long it is. If you have to do a truth table for that, and it goes on in principle forever, you can't list your pieces. Why? Because how many are there? Infinite. In which case you'll never complete your truth table. That's why for the second half of the course, when you introduce quantifiers, truth tables are out. We're not just dumping it for no reason. You can't do it. All right? Okay. And that's all you're turning in. That right there, that's world 10.22. The universal is like an and, but not the same.
And you
the
don't need...
existential is like an or, but not the same.
Do you need the sentences to go
Nope.
in? Just the world?
Just the world, that's it. How nice and easy.
So do we say that as sentences?
Just as world. World point 10.22.
I like you,
World
but I
10.
don't trust that smirk.
You don't trust that smart, something's around the corner? Oh, something's around the corner, just not what you think.
So everything is white.
Not all smirks mean it's bad. That means some smirks are not necessarily bad.
Some
Oh,
smarks are
get it.
zorks.
No, we're not doing last time. Smirks, smorks, forks, zorks. We good? Can I close this?
Yep.
Yes.
Okay, going once, twice, everyone got it?
Yes.
Bye-bye. Okay, 10.23 is next. Null quantification sentences. Okay, actually, you know what? Before I get into this, let me actually give you that lecture right there on the axiomatic method, and then I'll come back to it and I'll use it in the lecture a little bit. So axiomatic method, this is actually what frames the whole course, even though we haven't talked about it before. The notion of an axiom, some of you have heard of this, some of you haven't. If you took Euclidean geometry, if you took geometry in high school geometry is Euclidean geometry, after the guy who created that, Euclid. And it's basically a way of, it's an image of reasoning. It's a way of approaching a subject matter and trying to find the principles that underlie whatever it is you're studying. This image is so powerful, it's been passed down through time, and it still informs not just our education system, but the very notion of what a science is, how it works, and so forth. Okay, so So let me step back a little bit and just do it bit by bit. So axioms, you can think of them as the rules governing our universe in particular, right? They're general principles that have to be true no matter what. Remember we talked last time about TW necessities, Tarski-1 necessities, things that govern our world that have to be true no matter what, in terms of the way in which we set up the system. So everything is a TEP or cube or dodec. Another one would be everything is small, medium, or large. There's a whole bunch of them. But the point is these are sort of generalities that encompass the rules governing how the system works. If you want a parallel example of this, think of like if you learn a new game. Checkers, chess is a good example, right? Chess, when you first learn it, what did they tell you? If you haven't played chess, don't worry about it. But everyone has more or less had exposure to it, right? How does it work?
You want to collect pieces?
Yeah, you got pieces on there and then they tell you,
Take it.
The object is to get the king.
Get the king.
yeah, good, but before they do that, they say, here's a pawn, here's how it moves, right? Here's another one, here's how it moves. If it moves that way, you can eat it. The object is blah, 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 right? So the rules are, in a sense, how the thing moves, right? And the overall goal is what you're using those moves for to achieve, right? The axiomatic method says, here's the overall encompassing general rules, encompassing how this thing works, and everything that governs within that sphere, that universe, falls within that. Kind of makes sense? Okay, let me use a parallel example. Euclidean geometry is framed by this axiomatic method. Let's go through these one by one. This isn't totally accurate, but good enough for our purposes. If you haven't taken geometry, again, don't worry. So 1 says, between any 2 points, you can draw a line, form line segments. Seems obvious, right? Sure. Another one says you can take those line segments, this again is not totally accurate, but good enough. You can extend them out indefinitely to form lines, right? This one says, this is not the sign for contradiction. This says you take any 2 line segments, you form it like that, that forms 90 degrees, what is that?
Right angle.
Right angle, you can form perpendicular or right angles, right? You guys need this like if you go into carpentry, you need some basic geometry, especially, you can do it initially with just like measuring and tape and sort of eyeballing it, but you want more complex structures where things got to fit together exactly, otherwise you're screwed. You need geometry to some extent, especially when engineers, architects and whatnot, they're designing big buildings, they've got to use some basic maths and basic geometry to put these things together. Kind of make sense? Okay, so that says 90 degrees, you can form that. This one says, take a line segment, rotate it like a clock, you can form a circle. Obvious, right? This one's actually the controversial one, even though it doesn't look like it. This is called the parallel postulate. It says, take any 2 lines, like a railroad track, right? Drop a line between them. If they form both of them 90-degree angles, are they going to meet?
No.
No, they'll never meet. So it says 2 lines are parallel when, if you drop 2 lines between them, they form 90-degree angles. They never meet, they go on. They're parallel, right? So that one, sure, makes sense. This stuff, for those who did high school geometry, do you have good memories of it?
No.
Anyone? No, most of you are like, I don't remember it, it's a bad memory, it's a nightmare, I've forgotten it, I've repressed it, right? Or whatever. Okay, if you had Fitch back in the day, here's the image. For those who didn't take it, that's okay. But if you had Fitch back in the day, you can enter in, there's ways in which you can encode this into logic. You can add them up here as your axioms, okay? And then any particular problem you have, like for instance, if you remember, they say, show that this triangle is congruent to that triangle using side angle side or whatever. There's a whole bunch of problems you can do, right? Given these axioms, this is like saying, okay, I have a subproof within there, assume this stuff. You got this triangle and that triangle, and then dot, 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 there's some reasoning, and show that these two are congruent. You guys with me so far? If you had Fitch back in the day, here's what this axiomatic is getting at. You just cite these axioms, you highlight them, you highlight each of these, you anacon it, and this thing would come out as a check, and you'd show, yes, it's correct. The power of the axiomatic method doesn't just stem from the checks you get, though. Here's the image of reasoning. It's saying you've reduced all the complexities in geometry, all the pain you went through, all the difficulty of doing those proofs, and those are our original proofs. What we're doing is the logical structure of how those proofs are formed, okay? All the pain you went through, it's actually governed by nothing more than this deceivingly simple set of axioms. So this actually generates, if you think about it, the full span, the full range of possible things you can prove within the geometric universe of Euclid. Everything that you've seen, all the pain you went through in the book and far beyond, they're all within these boundaries. Kind of good? Okay. This image of reasoning is powerful. It gets passed down through time, and it is a kind of image. It gets passed down through time in the search for what's called first principles. Sciences are supposed to pursue the sort of most economical principles that unify everything together, but no, as it were, no less. Yeah. So the maximal complexity, but not with all this added junk. They want efficiency and simplicity, but not so simple that it doesn't capture what you're after, right? That image comes from this axiomatic method. So in the sciences, for instance, there's a pecking order. What's the fundamental science?
Plus and minus.
No, the most basic of sciences. Consider the master. Huh?
Natural.
Sure. Within the natural sciences, what's the most fundamental sciences? What studies the generality of everything?
Biology.
No, biology is just life.
Physics?
Physics, there you go. Physics studies mass, matter, motion, everything, including biology, is governed by these things. So physics is considered the fundamental science. What's built on top of that? Matter in motion. No.
Chemistry?
This is the line between natural, below. Yeah, there you go. Chemistry. Chemistry is physics applied to molecules and whatnot interacting, right? What comes after chemistry?
Biology.
Biology is the subset of chemical processes, but you're talking about life processes. This is not totally accurate, but good enough. We good? And then after that, it gets kind of fuzzy. There's mixtures in these things, by the way, but this is the general thinking of, you can think of it as pecking order. Beyond biology, you get, these are the natural sciences. They study the natural order of things, right? Beyond that, you get what are called the social sciences. They're sometimes called the soft sciences. Not because they're soft and easy, but because they're not as rigorous and difficult. They're kind of like fuzzy. People have these theories that it's not clear if it's totally true. If you read Freud, for example, women, what do you have? Those thinking psychology?
Hysteria.
No. Okay, men have a, what do we have?
You have Oedipal complex.
There we go, Oedipal complex. What does that mean?
You were in love with your mother.
Not just in love with your mother, but you want to?
Well, I'm trying to be
Yeah,
discreet.
there you go. You're trying to be very nice about it. You have strong...
You want to fuck your mother.
Okay, thank you. That's what it is. I didn't say it, but exactly right. And women, what do you have?
Daddy issues.
No. It's more screwy than that.
I'm sorry.
Uterus issues. We have a uterus.
So you want...
We want to. Oh, penis issues.
There you go. You want one, but you lack one, right?
Right.
So and you're like, where's this coming? Is that really science? But that's the problem. In the social sciences, you got all these theories, but how do you verify them? How do you test them, and so forth? There's some standing there, but they're not as sort of factual as these, right? As you climb the hierarchy, things get fuzzier. That's one way of saying this. They're soft. They're like not so good. Another way to approach it, a more charitable way, is to say, look, you're dealing with complexities here, human affairs, emotions. All these things are hard to track. They're not like physics where you're looking at a rock. The rock will only do as a rock does, right? You got people that screw things up. They can choose, they can act like a rock or not act like a rock, right? So there's complexities, yeah. So what you got is, respecting that complexity, you got as a result theories that try to accommodate this complexity, but as a result they're also not as rigorous as what you're going to find in physics and so forth. Kind of make sense? Okay, here's where we're going with this. The axiomatic method forms a way in which this pecking order sort of comes about. They want the maximum amount of, they want something that's unified. They want something that gives you the maximum amount of coverage in terms of the theories with a minimal amount of theoretical baggage. So all of these do that to some extent. When you get up here, it gets a little bit fuzzy. So you often hear, if you guys go into psychology, for example, they say there's too many theories out there, too many pet theories. We want first principles. That talk of first principles, trying to sort of reduce all that complexity to something more concrete, sort of, they can work from this base and then make it into a science. That comes from this image of reasoning. We kind of good? Okay, how does this relate to what we're talking about here besides this image of reasoning? The natural pecking order applies in a slightly different way. I'll come back to that picture in the homework. Let's get to an application. Let's shift gears slightly. This thing right here, you find that to be obvious?
Yes.
That two lines, if they meet at 90 degrees, they'll never meet? Okay, let's try something different. Suppose I tell you, you got two lines. I draw a line between them. They're both 90 degrees, but they do meet. Does that make any sense to you?
Yes.
If you say yes, what does that look like?
Like a curved circle.
There you go. Yeah, most people think that makes no sense, but if you think about it, think of our Earth. Here you are on the equator, right? Say we're here in Hawaii. Suppose we're exactly on the equator. You walk straight up 90 degrees. Where are you going to go? Where are you going to end up?
Alaska.
Not just Alaska, but the North Pole, right? Suppose I'm over here in California. I go straight, assuming you can walk straight up, right? 90 degrees again. Where am I going to go? I'm going to meet at the North Pole. So what they did was, there were some mathematicians and geometricians and logicians around the turn of the century. They said, let's deny this postulate and let's just prove stuff coming out of it. Initially they thought, this is crazy, this makes no sense whatsoever. It's just like total made up crap, okay? So they said, let's just do proofs and see the structure, the contour of what this mathematical system looks like. They call them non-Euclidean geometries because they're denying this, right?